Guys, we were discussing the suppressor. All right. And I showed you a couple of images in the past couple of videos of what the suppressor looked like on the inside of the instrument. So again, don't be thrown off when you see some of those pictures on the upcoming test because they're going to be there. All right. So now we need to talk a little bit about the theory of how the suppressor works. Maybe a closer look at what's actually going on inside of that piece. So first, what you have to understand, and we've said this before over and over and over, we are using mobile phases. And these mobile phases have ions in them. And these ions could be cations and they could also be anions. And we have discussed over and over and over that the cations can be picked up a little bit easier. And the reason is because they carry a much higher conductivity value as they go across that detector. So that's why we don't have to have a suppressor to measure those cations. Well, if we've got mobile phase, and that mobile phase is getting pumped through my system, and let's say here is the detector of the instrument, and this mobile phase is making its way through, and if the mobile phase is untouched, then these will have positives and they will have negatives loaded all in them, all the way down throughout that instrument and out the other end. And this detector is going to create a signal. All right, well, what that means is that your conductivity is going to be extremely high. And that we don't want, especially if we're measuring anions. If we're measuring anions, then these things are super weak, and we have to pump them through a suppressor, and that's to get rid of all of the cations that might be present. Anything that causes a high conductivity value or a very high signal will have to be removed from the instrument. So that way, when these weak little bitty anions come through and they peg a positive signal on the detector, we can actually see them. So, like we said before, the suppressor's job is to lower the signal of the detector. And the reason is because it's the cations most of the time that's creating this disturbance that we want to remove. And the suppressor will do its job in a couple of different ways, depending on the instrumentation manufacturer that you've got. So, overall, the purpose of the suppressor is to look at the mobile phase and remove the cations out of the system. That's what we want to done. That's what we want to do at least, right? So this leaves us with all of the anions that are there. And now you're probably wondering, well, what about the anions that's present in the mobile phase? I mean, isn't that an issue too? Well, the answer is yeah, in the beginning it will be. But there's a way that we fix that, right? So for this reason, every time that you use a suppressor on the IC instrument, it will always come after the column. After the column separation is typically where you will find that suppressor. So these components will already be separated. They will be coming through one by one. They will go into the suppressor unit. And when they go into the suppressor unit, they will get suppressed. And then out the other end, they'll eventually go to the detector. That's the steps that will always happen in an ion chromatography system. The suppressor is always placed before the detector. And I've said it over and over and over, but I'm going to write it real big here. It is only needed for anions. That's it, folks. Just anions only. So we have to think of the suppressor, and we've mentioned this before as well, but we've got to think of the suppressor as three different chambers. All right, I'm going to put chamber number 1, chamber number 2, and chamber number 3. And I'm just going to kind of draw these lines that kind of go back here. And there's something different that's happening in this suppressor unit as the system is running. All right, and we need to talk about each one of these. Step number 1, I want you to regard this area as the one that's getting your sample. So your sample is going in, and it's mixed already with the mobile phase, and it's going through chamber area number 1, and the suppressor is doing its job. And I want you to think of this as almost like a mini column. It's not really a column, but I think that if you think of it as a column, I think it will help you understand what's happening here. Because in the chamber, in each one of these actually, but in chamber number 1 that we're focused on first, if we think of this as a mini column, then that mini column will probably need a stationary phase. And it does. It's got one. No big deal. And this stationary phase has functional groups on it, just like the stationary phase in your main column. And these functional groups have the opposite charge. So if we want to remove the positive species, then that means that this stationary phase, these particles on the stationary phase, well, they probably need to be negative. And that way, when all of these cations from your sample and mobile phase come into the picture, and you want those cations removed, these cations will kind of get lugged and stayed behind. And they'll associate with these stationary phase particles that have these strongly negative groups on them. And the positives begin to kind of sit down on these particles, and they don't really move. They don't go anywhere. They get stuck. Well, all at the same time, your negative pieces that's in your sample, because that's eventually what you want to measure, those can actually escape on through the suppressor, and they can go out the other end. So these functional groups help remove the ions from the mobile phase that you were using on your instrument. And again, most of them are positive ions because they carry large signals, and we want a super low baseline when we can find one. Now, just like with a column, these stationary phase particles, well, they can get dirty, and they need to be cleaned. And sometimes things are going to be very hard to unstick. So we might need an extra oomph in order to clean out the suppressor sometimes. But as long as we have a general routine maintenance of a very good wash and a very good rinse, then our suppressor should be suppressing the signal for a long period of time. The suppressors that you'll find on the Metrome instruments, they last about 10 years. They have a 10-year warranty on them. So at any point in time, if that suppressor malfunctions or if the suppressor doesn't do its job anymore, then Metrome will actually send you a brand new suppressor for free if it's been less than 10 years since your purchase. All right, so all of that's happening in area number 1, okay? Your sample in your mobile phase is going through area 1. It's packed with stationary phase. This stationary phase is a negative surface, so all of your negatives in your sample will whiz right on through because they hate those negatives. And the positives will kind of get stuck behind, like a piece of fly paper. They get stuck, they can't go anywhere, they can't go out the other end. So the next step of the suppressor, we got to kind of scratch our head for a minute, and we've got to say, okay, well, what happens now, right? What happens when these things get stuck? What should I do as an analyst to make sure that my suppressor is actually doing the job that it's supposed to do? Before we talk about that, because that's going to be area number 2, I just kind of want to follow up on the rest of the negatives that are inside of your mobile phase, right? We don't want to forget about those. I've mentioned those, and I don't want you to kind of ignore that and just set it to a side. Most of your mobile phases are bicarbonate and carbonate mixes for anion analysis. We also have hydroxide as well, NaOH or KOH. And sometimes every now and then, we didn't talk about it, but if I have to pick out a third, this is going to be a tetraborate. And the tetraborate is going to be tetras 4. Borate is kind of a boron-containing group. It's B4O9. And that carries a -6 charge. All of these, though, come with potassium or sodium. Sodium bicarbonate, sodium carbonate, sodium hydroxide, potassium hydroxide, sodium tetraborate, potassium tetraborate, you name it. It's probably going to be a salt of a sodium or potassium. All right, so the suppressor is removing these pieces. The sodium carries a positive, the potassium carries a positive. These have very high signals that are going to be associated with them. So if these escape the suppressor and they go out into the detector, what you're going to see is an elevated baseline that's going to be way up here above a 0. And we don't really want that in anion analysis. So chamber number 1 is going to take care of that in the suppressor. But what about these others? Right? This is something that I've mentioned. And I said, well, if our job is to kind of go through and measure certain things, then these are all negatives. I mean, hydroxide is a negative, bicarb carbonate's a negative, the tetraborate is a negative. So are we going to see a signal that's based on these negatives? And the answer is yes, you do see a signal. That is why your signal is not perfectly 0 on the detector. All right, we've already talked about the range that the baseline should be in, and it should be between 10 to 20 microsiemens per centimeter. That is the typical conductivity value that we're going to always see on an IC system for the anion side of the house. And the reason that you're generating a little bit of signal here is because some of this stuff is coming through, and there's nothing that you can do about it. And this is constantly coming through, right? So it's not really separating in the column, per se. Your sample is, but the mobile phase is going through continuously, over and over and over and over. And that's kind of the purpose of the equilibration. It's just to get everything saturated with mobile phase, get the mobile phase pumping through, and you're going to create a little bit of signal due to these small little anions that are on the back end of the house. Okay, well, the problem is that if you use too much of any of these, then this means more bicarb, more carbonate, more hydroxide, more of the tetraborate, and this is going to create an enhanced signal. So you know if your mobile phase is correct just by looking at this signal that you're going to see from the detector, bottom line. If this is over 20 and let's say we're at 40, 50, 100, and nothing's pumping through and we're on the anion side, then that means it's not happy with the mobile phase. Either the suppressor's crapping out or it's not happy with the mobile phase. So the easiest thing in the beginning is change the mobile phase. And then you'll take a look at your suppressor to see if that one's getting ready to go faulty. So at the same time, though, I want you to understand that these just don't all go through as negative species. What that means is that ion exchange is taking place in chamber number 1. So I've got this particle, and this particle's probably got some negative on it. And this particle is going to have some hydrogen that's going to be on the surface of this thing. And that's just kind of its ready state. It's saturated with hydrogen. Why? We'll see that in the next video. But if my sample comes through and my sample has this sodium, sodium's kind of a bigger boy than hydrogen is, and sodium's a bigger bully because of that. So sodium can come into the surface of this particle and says, I'm here to stay. And hydrogen, you're going to be kicked, and hydrogen will go off, and it ventures off into the mobile phase that is passing through chamber number 1. So this is our ion exchange capability that's happening not in the column, but on the inside of the suppressor. So sodium's going to stay behind, hydrogen gets dislodged, hydrogen goes into the mobile phase, and inside of this mobile phase, we maybe would have hydroxide. if we use the hydroxide species for our mobile phase. Well, this H and the OH is going to come together and out pops water. And guess what, people? That does give you a zero conductivity. That's good. If we're using the carbonate, CO3 minus 2, well, a hydrogen could come around, and that hydrogen can make a bicarb, HCO3 minus 1, and that gets spit out. Well, that carries a little bit of conductivity. Not much, but it does. And then if we have HCO3 that's coming out, and we put H2 into the picture, then we can kind of make carbonic acid here. And if that carbonic acid stays together, then that carbonic acid is not going to create a charge, H2CO3. But a lot of times the carbonic acid could break down into water and CO2. Well, water's not going to carry conductivity. CO2 is just going to be somewhat of a gas that's going to bubble out. No big deal there. So this is what's happening to the anions that are located inside of your mobile phase. We're not talking about samples, but inside of the mobile phase. So you're probably wondering, well, what about the anions that might be in my sample? And the answer is, yeah, it could happen to those too. I mean, those are negatives. Those are pumping through the suppressor. Those could react with the hydrogen. And we could see some dampening of the signal. Well, that's something that we can't control. That's also some reason why we can't go as low as we would like to go sometimes on chromatography. And it's going to really prevent some of our analysis from happening on the very low levels. So if we just have a little bit of an anion, and that little bit of an anion gets some hydrogen slapped on it, then all of a sudden that little bit of an anion is not a little bit anymore, it's a little bit littler. Hopefully that makes sense. So the suppressor does suppress. The suppressor suppresses the signal. And it does that by ion exchange, converting those cations in the mobile phase and replacing those cations with hydrogen. And typically, if we're going to create something, it's going to be a very low conductivity acid, if anything. If it's not neutral, it's going to be a very low conductivity acid. Carbonic acid will go through, water goes through, the tetraborate side of the house, boric acid goes through, and all of those are super, super low. All right? Okay, so in the next video, we're now going to talk about what happens after this takes place. So after chamber 1, and let's say our sample's finished and everything is pushed through, then how do we replace this suppressor unit and get it ready to do its job for the second sample that I want to inject?